On behalf of Space Education and Research Foundation, and on my personal behalf, I welcome again Dr. Ritesh Kumar Mishra and all the participants of this webinar on the origin and evolution of the solar system. Today is the fifth talk, which is also the last talk of this series, and it's going to be on a very interesting topic, a million sun at the beginning, and that in the formation of the sun and the solar system. And before I hand over the mic to Dr. Ritesh Kumar Mishra to deliver this talk, I would like to mention that today being the last talk, the participant, whatever doubt or comments or questions they have of this talk or the previous three talks, they can ask those questions today, and Dr. Ritesh Kumar Mishra will be very happy to comment on those. And Dr. Ritesh Kumar Mishra has been a very good teacher for this webinar, and he had a very excellent academic career in school, college, university, and during his research work, his PhD at Physical Research Laboratory, and later has done extremely good work at several research centers in the world. And with these few words, I now request Dr. Ritesh Kumar Mishra to start his talk. Dr. Ritesh Kumar Mishra, please.
Good morning, everyone. Thank you, Dr. Watts, for giving me this opportunity to present yet another discussion on the origin and evolution of the solar system. In the fifth and the final discussion session of this series, we'll be talking about a million sun at the beginning, which is a rather figurative way of saying that the sun was about 1 million times stronger in its intensity compared to what it is today. So what we have previously seen is that of the more than 4,000 exoplanets, the planets that we have discovered around 4,000 exostars, we see that only one of the planetary systems have got 8 number of planets as that of our sun, which is Kepler 90. And although it has a equal number of planets, its architecture is very different from what we see in our Earth. We also saw that despite these differences, there are a few potential candidates which have a condition very similar to ours and which could host life. So since we know a great deal in much more meticulous detail about the formation of our Earth, if we can understand our formation very well, then we can probably apply the analog, the understanding of our formation of solar system to other planetary systems to say whether there would be life and of what kind, and to a larger general question of evolution of planets on different stellar systems. In that we in the first talk we saw whether the collapse or molecular cloud is a natural or a triggered one. In the second one we say we saw how the homogeneity and heterogeneity in our solar system is created, at what point of time after the injection it starts to become homogeneous, and then again how does it get the heterogeneity as the star continues to evolve through pre-main sequence stages, and then how the formed solids mix together to generate the diversity that we see in composition, in elemental composition, as well as the isotopic diversity that we see in a number of objects. So today we want to take a look at how active the sun was when it was born. So typically sun-like stars have recently been observed, or it has been hypothesized for a long time and has been observed, that sun-like stars are very, very active during their birth. So during their birth, they emit on. They are very active in terms of the mass that they are creating, in terms of energy that they are dissipating, in terms of X-rays, UV that they are giving, and that have obviously consequences on how these solids are forming, mixing together, are getting transported in the entire planetary system. What is of specific importance over here is that although the lifetime of a sun-like star is about 9 billion years, of which we have almost lived 4.5 billion years, the grand architecture of solar system is established in a very short period of time, in a relatively very short period of time of a few million years. So it is within the first few million years of about 2 to 5 at max, during which the growth from a micron size to a kilometer size of objects takes place, and then for next 10 billion years, or for these 4.5 billion years till now, the objects have remained more or less in the same form or in the same grand physical architecture that we currently see. Therefore, the events that are taking place in the very beginning actually determines and sets the condition for a later evolution of a planetary system which would be able to host life. So, for example, as an example, if I were to say, if Jupiter or if Venus or Mars were to be a slightly bigger or a smaller size, which they get within the first 2-3 million years, then the conditions on these planets, both Venus and Mars, they are almost at the edge of habitable zone around our sun-like stars, would have been very, very different, and therefore they could also have hosted life just like we have conditions for life on this Earth. So it is within the first 2-3 million years that almost all the conditions are more or less set that will eventually see the formation of life just about 4 billion years later. So 4 billion years later, like in our case, the explosion of life took place at the Cambrian era, which is about 542 billion years, and we are presently 4,567 million years. So a condition is set in the first 2 million years for a subsequent evolution of next 4 billion years. After the passage of those 4 billion years, the conditions for life would be so conducive that there would be a sudden explosion of life going on all the way from unicellular, multicellular to the complex kinds of life that we see today in plants, animals, and everywhere. So obviously, this condition is set by primarily driven by the sun, and so it is of critical importance that we try to figure out how the sun was behaving right at its formation. We statistically know how a sun-like star would behave, but as you have seen that any of these events happening slightly earlier or later can very dramatically change the structure. Therefore, we want to know specifically for our sun what kinds of events happened at what time period in what particular sequence that created this kind of a texture, architecture, or that helped build up these kind of complex chemical and physical characteristics. So in this talk, this is the third in the series. We have already talked about the two. Today we'll be talking about the radiation state during the initial stage. We'll be talking of a short-lived radionuclide 57 beryllium, which decays to 7 lithium in a very very short period of time of 53 days, about 2 months, and thereby we will be able to establish the life of sun for a year's time, 4.56 billion years ago. But that would be the attempt to establish the so this is the summary slide where we will what we will try to achieve at the end of this talk. So by studying the radiogenic decay of 7 beryllium into 7 lithium and looking at that record inside a few millimeter size object called calcium aluminum rich inclusion, we will first establish the presence of 7 beryllium, and then by establishing the presence and abundance at this level, we will be able to conclude that the formation of this solid should have taken place by the intense activity of early sun. There should be multiple episodes of such high irradiation or high intensity of activity by the sun. This should have primarily taken place at the end of class 1 or beginning of class 2, which is a rather later stage at which sun gets very, very active. And this will have consequences on how solids are formed, are being mixed, and are being transported in protoplanetary disk within the first few million years. So this CI is made by a million sun. It's a rather figurative way of saying that this CI, a few few centimeters in size, was created by a sun which was a million times stronger than the most intense or the most intense sun that we currently see. So the X-class flares that we see currently from sun, the intensity of sun at that particular, in the beginning of the solar system, was about a million times more than the X9, X10 class of flares that we currently see. This paper was recently published in Nature Astronomy. For several, most of the details I'll talk about, but for several details, I welcome you to go and take a look at that paper. I'm happy to answer any of the questions that you might have, not just of this talk, but of previous talks, and I hope I'll be able to give a explanation or give my understanding of how those events and things took place. So as I said in the last two talks, we have been talking about what is called as short-lived, now extinct radionuclide. If we look at isotopic records of the meteorite, we see that that of the several possible radionuclides, we have confirmed evidence of about 14 radionuclides that have half-life in the range of a few days to a few 100 million years. Their decay, this table shows those short-lived radionuclides. About 14 of them have been confirmed. The 15th one is the one we are going to establish today. In this table, we see their half-life, the daughter nuclides in which they decay, what is their inferred solar system initial abundance. So we want to know at what was the original number, what is the number at which what is the corresponding number when the solar system was forming, or at the time when it starts to form, so that we can tag different events by the number that we see in the object. So so these have been some of the one that we'll be talking today would be 7 beryllium. I have said a few words about it already. So 7 beryllium has been proposed as a proponent of as an example of radionuclide that is created by irradiation or spallation reaction. So oxygen and carbon nuclei can be relatively easily broken down into smaller nuclei of 7 and 10 beryllium. They have been so 7 and 10 beryllium are primarily considered as the nuclei that are created by spallation reactions, spallation which could be induced by the energetic particles given out by sun during the during its active or a normal state, or also by the galactic cosmic rays. So this table, this plot shows several short-lived, now extinct radionuclides and the sources from which they can be generated. If a particular nuclide, like 7 or 10 beryllium can be generated just by irradiation source, then obviously then we can fix the amount of irradiation, or we can fix the intensity of radiation, and thereby have an important constraint. Similarly, there are other nuclides which are produced only by the stellar source, and therefore they are a useful traces to understand what kind of star contributed how much material to our solar system. However, to my mind, it seems that 7 and 10 beryllium has wrongly been all the time ascribed to just irradiation spallation process. For way back in 1988, 1990, it was rather tentatively, or rather sufficiently well enough known that they can also be produced by the neutrino reactions in the helium shell of an exploding supernova. So, so the discussion or argument were swayed in the favor of irradiation spallation by overlooking the fact that 7 and 10 beryllium or the lithium beryllium boron could also be created by a supernova event. So why this argument was favored over the other? Because if you look at the binding energy curve per nucleon, we see that both lithium, beryllium, boron have a very low binding energy, and therefore, in a very general scenario, inside the stars, they are usually get used up as a fuel rather than being created. So, in the process of nucleosynthesis or building up of nuclei of larger and larger masses, because of their smaller binding energy, the temperature inside the core of the star or in the adjoining shells are typically very, very high, that these nuclei are not stable enough, and therefore they are not created during nucleosynthesis of star. In a typical general scenarios of nucleosynthesis of star. And therefore, if you look at the abundance of these elements in the solar system, we find that their abundance is very, very low, is 5 or 6 orders of magnitude lower than what would be expected, what is seen for the other nuclides in its neighborhood. For example, helium, carbon, oxygen, and nitrogen, which are the carbon, oxygen, and neon, which are the major products of supernova nucleosynthesis. They are about 5 or 6 orders of magnitude higher in abundance than lithium, beryllium, and boron. So this is a summary slide of what we know about what is generally known about how elements are synthesized inside the star. So we get hydrogen and helium. Most of the hydrogen and helium comes from the Big Bang, which we saw in the second talk. The elements from lithium to boron are believed to be forming mostly by cosmic rays. We'll see how this creates a little bit of complications into the story that we're going to say. And then from carbon onwards, all these elements are primarily made up inside the star, with the more massive ones beyond iron, especially made during the supernova events of different types. So how did this story came about? So although short-lived radionuclides were discovered in 1917 itself, most of them were the initial ones that were discovered suggested that they should have, because they were large, they had a large atomic number. It was believed that they should have been formed inside the star and injected into the solar system. However, the story took a dramatic turn in year 2000 when McKagan et al. Showed that by analyzing a CI in LND, showed that there was an excess in 10 beryllium in this CI, which correlated with 9 beryllium by 11 beryllium, thereby providing an evidence of presence of 10 beryllium in this CI at the time of its formation. So once 10 beryllium was established, presence of 10 beryllium was established in the CI, it became imperative from the previous argument that we just gave about the formation of elements, that irradiation in the early solar system must also be contributing a significant amount uh, that is that should be accounted for, and that leads to the formation of 10 beryllium. However, it is important to note that it has a half-life of 1.387, henceforth we'll say 1.3, 1.4, 1.39 or 1.4 million years. Therefore, it would continue to exist for 6 or 7 half-lives, which would mean about 6 or 7 times of 14 would be something like uh, 8 or 9 million years. So these nuclei can exist in the early solar system or prior to formation of early solar system by 8 or 9 million years before it gets incorporated into the CAIs. So following this study, a more extensive work on the same CI was done, and subsequently an improvised number was given, which was 8.8 times 10 to the power minus 4. So by analyzing several other mineral phases, melilite, facite, these are minerals which are found inside these CIs. You could see different shades in this CI. So these phases this would correspond to pyroxene, this would correspond to melilite, this would correspond to anorthite. So these different phases which are present inside the CIs host different amount of beryllium boron, and therefore you can analyze them to get this kind of an isotone. A more precise one was done a few years later to establish with more conformity, with more strength, from which it was inferred that the 10 beryllium by 9 beryllium at the time of formation of this particular CI should be 8.8 times 10 to the power minus 4. However, in this study, they also studied the decay of another short-lived radionuclide, which is 7 beryllium, which decays to 7 lithium. It has half-life of just 53 days or about 2 months. They tentatively said that there is a plausible evidence of 7 beryllium by 9 beryllium at this level, 6.1 times 10 to the power minus 3. So 7 beryllium by 9 beryllium in the same CI, they found that there is a possible evidence of 6.1 times 10 to the power minus 3. They said this as a possible evidence because the CI had been analyzed previously for aluminium magnesium. Its mineralogy, its petrography had been previously studied, and they found that the CI shows a disturbed in the isotopic character in aluminium. It also shows secondary minerals which tend to form, which post-date the formation of CIs by a process of alteration or metamorphism. So therefore, they had to choose what data of the measured data, what they would choose to infer these particular values. So they used a criteria of crystallization from a primary melt to select the data set from which they would infer both the 10 beryllium and 7 beryllium. The data, however, was later shown to be so 7 beryllium and 10 beryllium, because they can be easily generated. Also, the lithium isotopes can be easily generated, and because these meteoroids tends to stay for a while in the are floating in the outer space before they land up on the Earth, the isotopic character of the meteorite is transmuted by the amount of cosmic radiations that they receive on them. And LND has a exposure age of 5.2 million years, and its size is expected to be about 50 to half a meter, which means while it was floating for these 5.2 million years, the isotopic composition is altered by the cosmic ray that the body is seeing. So what we have to do is what we see now, we have to correct for the cosmic exposure age that the body has seen. So that's how we arrive at the isochron that we currently have. So Lia et al. Showed that the corrections that were made by Chosidon et al., shown by the fit over here, light gray line, they had overestimated the correction, and they should have been ideally at this line. So lowering the excesses in the major, in the ones that were showing larger excesses meant that the isochron was no longer fully resolvable. Also, by the statistical analysis of how the data is distributed, Lia et al. Concluded that while there is a correlation, a linear correlation cannot be said between the data because of the residues that that the data set shows. So there should be some other process other than the analytical uncertainty that are associated with it. Therefore, a linear correlation between the data sets cannot be established, and therefore a linear argument of presence of 7 beryllium was put under threat. However, subsequent to this CI, several other CIs by several other groups were also found to contain 10 beryllium by 9 beryllium. I'm saying 10 beryllium by 9 beryllium and not 7 beryllium by 9 beryllium. In a several objects were found, and it was found that they do not correlate with the age of formation, which is typically inferred by 26 aluminum by 27 aluminum, which was more or less expected, and therefore they said that this kind of an discordance between the age and the amount of 10 beryllium and 9 beryllium can be very easily explained if the sun is irradiating it. So depending upon where the CI is, or depending on what time the CI is forming, the intensity of sun would give you a very different amount of 10 beryllium by 9 beryllium in that particular CI, and therefore there is no correlation expected between the age of the CI and the 10 beryllium by 9 beryllium. Typically, for most others which are created or generated in a homogeneous environment, we typically expect that there is a correlation between the age of the CI and the amount of radiogenic, the amount of short-lived radionuclide in that particular object. However, that correlation was not seen into these for 10 beryllium by 9 beryllium in these CIs, and therefore it was inferred that these CIs can be explained by mixing between a pre-irradiation solar nebula and an irradiated gas by varying amounts. So if we mix two solids, if we create solids by mixing between two reservoirs, then all this can probably be explained by irradiating solids by different amount and then mixing them in different proportions. So if you mix a solid which has been irradiated to a level of this and then mix a smaller portion of it, you would get something like this. If you had irradiated something at the level of 10 to the power minus 3, and you would have got something on this line. So that's how 10 beryllium was, the diversity or the range of 10 beryllium was not concordant with the age of the CI was explained. However, over this time there were improvement both in the astronomical observations as well as in the nucleosynthesis. And one of the observations made was that there is a linear correlation between the abundance of beryllium with several of the major products of nucleosynthesis. So for example, magnesium, titanium, oxygen, and iron, it was seen that the abundance of beryllium with abundance of iron matches a linear correlation, more or less a linear correlation over 3 orders of magnitude. And the same pattern is observed for other elements like titanium, magnesium. So from which it could be said, because these magnesium, titanium, oxygen, and iron are the major product of core collapse supernova, and if they have a more or less linear correlation with the beryllium over such a large range of about 10 to the power 3, then it hints towards production of 10 beryllium also by the more or less similar procedure or the same process that generates magnesium, titanium, oxygen, and iron. So we were looking, the signatures were looked by Postcard et al. And has been reported in this paper for 107 metal poor stars. So metal poor stars are where these which are older stars, and they also have a less ambiguity between what is the original character and what is uh, the character of mixing and subsequent evolution. So as I said initially, that the discussion was swayed or discussion was favored in the favor of spallation, although it was very well known in 1989 and by where Woosley et al. Had described a process where described a new process or the interaction of neutrino with helium shells to produce 711 beryllium and several other nuclides. So, however, they also noted that despite their consideration, they find that sufficient amount is not generated in the outer helium in the helium shells of these stars. But there have been continuous progress in the nucleosynthesis as well as in the way we know a lot more about neutrinos than we knew about 20, 30 years ago, and now these have been used into these considerations have made these have revised our understanding about. So Epstein, Colgate, and Hexton in 1988 had suggested the interaction of neutrinos in the helium shell that would give this kind of a reaction. However, they noted that lithium beryllium boron are primarily produced in very low amount. In the recent years, Yoshida et al. Have shown that the cross sections used over here for interaction of 4 helium to give 3 helium and for 4 helium to give 3 hydrogen have been revised to a larger number. Once these have been revised, they find that the amount that is produced, the amount of 6 lithium, 7 lithium, 9 beryllium, and 11 boron that are produced are increased by a significant amount, but at the same time, the abundance of 10 beryllium is lower in the 16.2 mass star that Yoshida et al. Studied. In revision to that particular work, a recent work showed that this is not the pathway for the R process, and in the real process which generates a large amount of N for R process is actually this reaction. And it is in this reaction that 7 lithium, 9 beryllium, 10 beryllium are produced in much more significant amount. So the work by Banerjee et al., they could show that the R pattern of our solar system, shown as the black line on the top, can be reproduced in a low and a medium mass stars with these revised values, and for those explosions which are slightly lower in energy than the typical supernova. So for a typical supernova, the explosion energy is about 1 Bethe or a few times Bethe, which is 10 to the power 51 ergs per second. But for a low 0.1 to 0.3 Bethe, for stars which explode with low explosion energy of the order of 0.1 to 0.3 Bethe, then this kind of an R process, abundance of elements can be reproduced. So if you look at these, if you look at the green and the yellow, green and the black line, you can see that this pattern of R process, which is seen in the elements in R star, is reproduced, very faithfully reproduced to a good extent. So this slide shows a much larger picture of the same, and it can be inferred that if you wait for the post shock for 15 and 20 seconds, then that pattern is very well reproduced for the and the neutron intensity in these zones are also at the required level of the order of 10 to the power 19 and 20 to be able to drive the R process that will generate those reactions. And in that process, the synthesis of 7 beryllium, 9 beryllium, and 10 beryllium takes place. So you can see over here that 7 lithium is generated in a large amount, 11 beryllium is generated in large amount in different zones and in different massive stars. So they gave 2 new primary mechanism for synthesis of 9 beryllium, and consequently the other nuclides around 7 lithium and 6 lithium, 10 boron and 11 boron. So they revised the mechanism which was previously suggested by Hexton and them. They suggested that the pathway that is followed for generation is this in the helium shell of these stars which explode with lower energy. We require lower energy, as if you remember, I said initially that they have low binding energy, therefore high temperature leads to breaking up of that nuclide. So if it explodes with a lower energy, then the temperature profile is lower and the neutrinos are, and if that is sufficiently high enough, then these process can take place, and the neutron source is this, and therefore for a low for 2 different mechanisms of where for a 8 mass star and for a 11 to 15 mass star, they showed that this process can lead to formation of 10 beryllium by the neutrino-nucleus reaction inside these stars, and therefore that very premise that 10 beryllium is only created by the spallation reaction lost its craft. So to show that they showed that several other nuclides can be generated from the stellar yields of the model which generates 10 beryllium, and from this they computed that if we mix a fraction which is about 4 or 5 times 10 to the power minus 4 and allow the ejecta to come to Earth, allow the ejecta to mix with Sun for about with the composition of Sun with a time delay of about 1 million years, then the abundance of 41 calcium, 10 beryllium, 107 palladium, and also 60 Rn at the lower level can be explained. So all this could be explained by yield from a star, and therefore 10 beryllium as a smoking gun for irradiation lost its ground. Obviously, this kind of a production has consequences which we saw in this slide. That when 10 beryllium is generated at this level, at the level of 10, on the mass fraction scale, at minus 10, 7 and 6 lithium are produced at a much larger amount. So a full circle came back, and that gave a motivation for us to study lithium, beryllium, boron. So we have these 2 isotope systematics, 10 beryllium going to 10 boron in 1.3 million years, because it is generated in 1.4 billion years. So it has about 6 to 8 billion years of time to be able to generate it and be incorporated inside the solar system. However, 7 beryllium, which decays to 7 lithium, has got a half-life of 53 days only, and therefore it has to be produced and incorporated into solid within a year's time. 5 times or 6 times 60 is about 360, which is about a year. So it has to be formed and incorporated inside a solid within a year's time to be able to preserve and be able to preserve that record for 4.5 billion years to be able to see it today. So this is a much stronger constraint. So we decided to study both the systematics in a CI to resolve that question whether the irradiation is the contributing source and whether the 10 beryllium that we see in the solar system comes from the stellar source or from the or from the yield of a star. So to do that, although this evidence existed way back in 2006 or so, but uh, so we looked at a CI which was relatively large, which had several primary characteristics, which was pristine, and which had, of the several CIs that we studied, we found that this CI would hold the potential for such a study. So this plot shows the magnesium, calcium, aluminium mosaic, whereby you can identify different minerals very easily. You can see this is a very large CI. The scale bar at the bottom shows it is about 3 millimeter in size, and therefore this is a very large CI by typical standard. It consists of malachite. The aluminium concentration decreases from outer rim towards the inner core. The magnesium concentration is increasing towards this side. In the core, we have several spinels which are relatively larger in size, a few 100 microns in size, which is a very large by typical meteoritic standard. Then there are some very rare anorthites over here, and they are hosted within a pyroxene, which is shown over here. Then the CI is fractured or broken at the other half, but the other half, it is faithfully surrounded by what is called as the Wark-Loving rim, which is a multi-mineralic layers of mineral which form when the outer region of a CI is rapidly melted and the condensation takes place, and the recondensation of minerals takes place. So these petrographic features, like the large spinel that we see, the magnesium end member, it being a magnesium end member, the titanium-rich content of pyroxene, the zone malachite character, this all shows that the CI should have formed from should have crystallized from a melt with a maximum temperature of 14-20 degrees. It should have cooled at a rate of about 0.5 degrees Celsius per hour. And most of the characteristics in this CI are primitive in nature, or as it had formed at that time. We will see the importance of having these temperature and the cooling rate in the subsequent slide. As you can understand, because we have only 50 or 60 days to form a CI and get it incorporated, all that, these cooling rates and the maximum temperature that it reaches becomes a very important criteria to determine and judge or to preserve those isotopic records. We'll come and we'll see that in the later slide. In this slide, in the following few slides, we'll just skip over. These are just meant to show how did we establish that this particular CI had all the had the right compositions and characteristics that would show a preserved record of 7 beryllium, which would decay to 7 lithium. So this shows that the amount of 10 beryllium incorporated in the CI was relatively higher compared to the CI which was studied previously. So if you incorporate higher amount of 10 beryllium, you have obviously incorporated higher amount of 7 beryllium and reduced the isotope of this, and therefore you are more likely to be able to see the excess resulting from the decay of 7 beryllium into that CI. So several tests have to be done to show that it is not a mixing line, or there are other issues as to they are only dependent on the correction, because I said we have to correct for the cosmogenic exposure of that particular meteorite. So sometimes the cosmogenic correction itself could predominate, and therefore the linear correlation that we see is just because of that. So to negate all those possibilities, we looked at all possible kinds of correlation between mineralogy, their isotopic signature, and the amount of different elements within and outside through several transverses to come to this conclusion that this CI, the excess that we see in this CI after the cosmogenic correction does not arise from either a mixing or from cosmogenic correction itself. If you remember the one of the reasons why there was a doubt about the previous work was because in a later work it was shown that the correction which was done for anorthite and pyroxenes, which were showing the largest amounts of excesses, they were revised downwards. They have been corrected. The correction that were applied to those were slightly higher in them, which generated the linear correlation. So we only analyzed malelite, and therefore, which was a rather difficult exercise because malelite shows a limited range of beryllium and boron. But by negating all these possibilities, we could show that 7 beryllium exists at the level of 1.2 times 10 to the power minus 3. We could also show that the intercept is quadratic. Intercept is quadratic means so the line at which it goes and intersects the y-axis is the composition of the solar system. Is this composition of the solar system, which is 12.02. It is a very important constraint because you could mix material somewhere from here, which would have a very low composition, or from over here, and then you can generate a linear line. Typically, a linear line can be generated by several processes. One of the prominent one is by mixing between two end members from here and here, expectedly. So having a quadratic intercept means that it could only be mixed by mixing something which was quadratic, which had the solar composition. In the same CI, we also obtained the 10 beryllium by 9 beryllium at the level of 1.6 times 10 to the power minus 3. This line shows the highest amount of 10 beryllium of 1 times 10 to the power minus 2 seen in some CIs, and this is the line which shows the 8 times 10 to the power minus 4 times 10 to the power 8 times 10 to the power minus 4 10 beryllium by 9 beryllium seen in the other CI where 7 beryllium had been studied. In this CI, 26 aluminium had previously been done by Goswami and his co-workers, and from that they had inferred that this CI had formed 26 aluminium by 27 aluminium to the level of 3.4 times 10 to the power minus 4, which would mean that this CI formed about 0.45 million years after the formation of CI. So this CI, the age of this CI could be inferred from aluminium magnesium isochrone work, which was done previously by Goswami. So one of the major reasons why such an isotopic record had not been obtained previously is the diffusion of lithium. So 7 beryllium decays to 7 lithium. Lithium diffuses very, very fast, like potassium and sodium. So typically, if you heat a mineral or a phase, the isotopic record would be mixed with the surrounding minerals and phases. Therefore, it is very, very difficult to be able to see these records. So not just its half-life, but a slight perturbation or a slight post-formation heating event could diffuse the isotopic records of lithium into surrounding, thereby making it difficult to observe these records. Over here, we have approximately estimated as to what should be the diffusion rate, because the diffusion of lithium within beryllium is not known, but the diffusion of lithium in feldspar is known. So lithium and potassium diffuse by these numbers or at these temperatures at these scales. So we have considered two scale, 50 and 200 microns, the typical size of the beryllium that we saw in the large CI that we saw, and the typical size that the analytical spot would have, about 20 microns, and the temperature it was. So the maximum temperature that the CI was heated was about 14-20 degrees So we have considered 1400 degrees. If we allow it to cool for, let's say, 50 days at 0.5 degrees Celsius, which was the cooling rate that we had observed for that CI, then within it would get down to 800 degrees Celsius within a month. So we see that at 800 degrees Celsius, which is what the CI would cool down within a month and would continue to cool, the isotopic record would be diffused only if it stayed at that temperature for about a year's time. So thereby we could establish that yes, that it has to be transported outward and get to a cooler environment within that time to be able to preserve those records. So this is an important constraint coming from the diffusivity. Now, once we knew once we could establish the amount of 7 beryllium and 10 beryllium with respect to 9 beryllium, the stable isotope of it, we went to calculate the amount. We went to calculate the scenario. We went to create the scenario which would generate this kind of which would generate the amount that we see in the CIs. So production of a radionuclide is the flux of the particle, the number of targets that we have, and the reaction cross sections. So we found out the reaction cross sections for these, and then we assumed the spectra of the radiation by varying their rigidity. We can assume what would be the spectra of particle. It is less shallower or it is more steep. If it is more steep, then you can see that it would have more of these and less of these. And because the production is dependent on the product of the number of particles as well as the reaction cross sections, you can vary the production of these nuclides which are produced. So we calculated the production of several short-lived radionuclides, and we fixed that the 7 beryllium in the observed amount should be produced, and then we found out that if we irradiate the CIs for a month's time, for a year's time, then 7 beryllium and 10 beryllium, shown by the green line over here, can be produced in a few years' time, along with 53 magnesium and 41 calcium, while the 26 aluminum and 36 chlorine for the assumed scenario having the irradiation spectra of gamma equals to 2 and composition equals to the solar composition, we could simultaneously produce 10 beryllium, 7 beryllium, and 53 magnesium and 41 calcium at the same level. So from this, we could conclude several things. We could conclude that because 7 beryllium has got such a half-life, there is no possibility for it to be produced outside before the collapse of molecular cloud and be transported inwards like the possible case for 10 beryllium. Therefore, the irradiation of material should have happened only inside the solar system. The CI had an age of about 0.5 million years, so that should have happened 0.5 million years afterwards, which is another constraint that the irradiation should have happened locally. Because it happened afterwards, and there are CIs which have 10 beryllium. We have CIs which formed earlier, but they also have 10 beryllium at time t equals 0. Therefore, there should be multiple events of irradiations. Because we see 7 beryllium at this higher amount, this event should have happened at the end of class 1 or at the beginning of class 2 stage of Freeman sequence stage. From that, we could calculate that the intensity of the irradiation at that particular time should be of the order, the X-ray intensity should be of the order of 10 to the power 32 ergs per second, which will produce sufficient amount of photons for these reactions to take place. So we need sufficient amount of neutrons to be able to generate these nuclides for the chosen spectra of all these elements, and therefore we need this kind of an intensity to be able to match the observed abundance that we see in that sphere. And this kind of an intensity, X-ray luminosity of 10 to the power 32 ergs per second, is about 1,000,000 times the X-class flares from the contemporary sun. Therefore, what we said about this CI is this CI is formed by 1,000,000 sun, or 1,000,000 sun at the beginning. When I say 1,000,000 sun, it doesn't mean that the intensity in the visible range is 1,000,000 times. The X-ray intensity or the particle intensity associated with the events at that particular time, lasting for almost an year's time, is about 1,000,000 times the X-ray intensity that the contemporary sun emanates today. So the most energetic X-ray flares that we have seen in the Carrington event, and some of the most intense ones that we have seen in the recent times in 2006 and some recent ones too, the X-class flares, the intensity of sun at it during the time of its birth was about 1,000,000 times higher than the ones that we have seen. Also from the lithium isotope, because it diffuses very, very fast, we could establish that not only the creation of that solid would take place within short time, it should also be transported to a distance far off, typically to a distance of about 1 astronomical units, where it would get incorporated into the parent body of carbonaceous contract that we see. So there should be a very rapid energetic mechanism for transfer of these solids to a distance of 1 astronomical unit within a year's time, which is a very rapid energetic mechanism by a typical standard. And therefore, we'll come to the end of this talk. I'll acknowledge some of the materials that I've taken from the web page and research papers to discuss several issues with this particular study. And I will acknowledge my collaborator, K. Pujit Kaur Barhat, whom this work was carried out. And obviously, I've had immense learning on this subject from my PhD advisor, J.N. Goswami, while I was a PhD student at PRL. And the other work, the other previous work, which was done by my postdoctoral advisor at Center for Sensitive Research, Petrography, and Geochemie at Nosy France. So I had a lot of learning on this particular subject from Mark Chosidan and J.N. Goswami, whom I thankfully acknowledge for sharing and having the discussion on this time. With this, I will stop, and I'll welcome any questions and suggestions, not just on this particular talk, but also on the previous talk that I gave previously.